2.4, zeros of polynomial functions. So we start out with the rational zero theorem, which should be review. And we are given a general form of a polynomial. So it looks like a sub n is our leading coefficient, it's degree n, all the way down to our constant term a sub 0. If it has integer coefficients, then our rational zeros have the form of p being a factor of a sub 0. So p is a factor of this, which is the constant term. And q is a factor of our leading coefficient. Q is a factor of this. I would write leading coefficient, but there's really not enough room here. So remember, when we talk about factors, they can be positive and negative. So remember, P over Q equals plus or minus. We don't want to forget about that. And remember, these are possible rational zeros. So it doesn't mean that they are all rational zeros. It just means that these are possible rational zeros. So we are going to use them as guesses. And I know that guesses is not a fun way to solve in math, but that's what we're doing here. So a lot of math so far has been devoted to looking at graphs of different kinds of functions and then also solving them. And that's really the heart of what we're trying to do today. We're looking at these higher degree polynomial functions. It's great if we can factor. Yesterday they gave us a factor of it and we finished solving from there. But what if we don't have any information to start with? What if we have a fourth or a fifth degree polynomial? What exactly do we do? And that's where we use this rational zero theorem. Other information that's helpful, upper and lower bounds. So a lower bound, just to kind of put this in our own words, there are no zeros lower than this. So when you get to a lower bound, you know not to keep guessing smaller numbers. So if we have a lower bound, we're checking a number with our synthetic division that's less than or equal to 0. And the last line of the division is alternating non-negative and non-positive. An upper bound is going to be the reverse then. Upper bound means there are no zeros higher than this. And I'm talking about like numerical value, like if our upper bound is 2, then 3 would not be a 0. It's higher than 2. It's a greater number. And for an upper bound, it means we're starting with a number for synthetic division that's greater than or equal to 0. And every number in the last line of the division is non-negative. So they all have to be non-negative. Notice it doesn't say that they can't be 0, it just says non-negative. So we're going to go ahead and try solving this first equation. So when we look at this polynomial, I see it's degree 4. My exponent's 4, 3, 2, 1, 0, so that's really good. I need to first look at P's and Q's. There's no way to factor this. It's 5 terms. I can't do factor by grouping or anything. We have no strategies for 5 terms. So P comes from factors of the 48. So that'll be a plus or minus 1, 2, 3, 4, 6, 8. There's a lot of factors here. 12, 16, 24, 48. Oh my goodness. Q is just going to be plus or minus 1. So when we look at our values for P over Q, we would have plus or minus just 1 in the denominator. So it's really all the same things as P. So plus or minus 1, plus or minus 2. Normally I write my plus or minus at the beginning and then use parentheses to kind of show it's all of them. But really we're supposed to write it this way. Plus or minus 6. It's just time consuming to write them all. And I have some students that unless we list these, you don't really understand what we're doing. So I'm not just trying random numbers, I'm trying these random numbers. I'm not picking 100 to try. I'm not picking 5 to try. I'm picking numbers that follow this pattern where P divided by Q, and P is a factor of the constant, Q is a factor of my leading coefficient. So now I'm going to try some numbers. I usually start out with the 1 and -1 and just kind of move through my list from there. So we'll start with 1, and my coefficients are 1, -11, 44, -76, 48, and we're just doing synthetic division. We're trying to see if it's a factor. And I'm not having a good feeling about this one. Let's see, 76, -76 plus 34 would be a -42. Nope, doesn't work. Let's try -1. And we should be getting pretty fast at our synthetic division. Let's see, 132. Okay, so no luck again. But I noticed something. What I noticed is that I started out with a number that was less than or equal to 0, and I have alternating signs. So what that tells me is that -1 is a lower bound. So the good news is now I can kind of refine my guessing. So I no longer need to check any more negative values because I will not have a 0 that's less than -1. So now I probably start with 2, right? That's my next number in the list. So we'll try 2, but I'm not going to try -2. I've already shown that -1 is a lower bound. We're not going to guess anything less than -1. So that's where those upper lower bounds I think are really useful. They help refine that guessing. So I've got my coefficients again. I needed to copy them a little bit before I move this page up. Let's see. Two times 26 is 52. It's like you go fast for a while and then you got to stop and think again. -24. Oh, look at this. And we have our first 0. So now I'm going to have, I started out with a 5th degree equation. So now I'm going to work with my depressed polynomial, or my depressed equation, because we're really solving it's equal to 0, so I could say depressed equation if I wanted to. So now we're working with x cubed, because I started out with 4th power, now I'm 3rd power, minus 9x squared plus 26 minus 24 equals, 26x minus 24 equals 0. So this is what I'm looking at now. And if I'm looking at 4 terms, sometimes I can do factor by grouping, but I can see like the 26 and 24, all I could do is factor out a 2. That's not really going to help. It's just not going to work for factor by grouping. So I need to just work with this new equation. So I'm going to have to look again at my p's and q's. They're going to be different now because I have a 1 here and a 24. So my p's are going to be plus or minus 1, 2, 3, 4. We're not getting rid of a lot of numbers, but we're getting rid of a few. 6, 8, 12, and 24. We got rid of 48 and we got rid of 16, right? Q is plus or minus 1. So when I look at P divided by Q, it will be plus or minus 1, 2, 3. So we want to think really carefully about what we try for this list. So if positive and -1 did not work with our original function, it's not going to work now. So I don't have to guess that. I also know that -1 is a lower bound. It's still a lower bound. So I'm still not going to guess anything that's positive or anything that's negative. But it is possible. I had 2 was a solution once. It could be a repeated factor. It could be a multiplicity. So I'm going to go ahead and try 2 again. I don't want to move on to the next number until I've made sure that I'm done checking with 2. So I'm now using my coefficients from my depressed equation. So 1, -9, 26, -24. So I'm using the ones from this equation right here. I'm not going back up to the beginning. Remember, we want to continually reduce this polynomial. Right now it's cubed. If I can find another 0, it'll be down to squared. That's what I'm trying to do here. I'm trying to make it into a quadratic because I have other methods for solving quadratics. I can always solve a quadratic. And I found a 0. How lucky is that? So it turns out that 2 was a repeated solution. So now I want to look at the quadratic that's left, x squared minus 7x plus 12 equals 0. So remember, if we start out with a cubic, once I find a 0, now I'm squared. And I can factor this, x minus 4 times x minus 3. And it says actually solve, so we're going to finish. The goal is not factoring here, it's solving. So x minus 4 is 0, x minus 3 equals 0. Please show these work steps. When I add 4 on both sides, and I don't need to show that part, I will now have x equals 4 or x equals 3. And now I do need to list out my solutions. So I know that my solutions were 2, right? And 2 was a repeated solution. So let's use our vocab here. It was a repeated solution. So that means x minus 2 is a repeated factor. And I'm going to also write that it has a multiplicity of 2. So if I was just writing out my answers, I probably wouldn't write this, but we are practicing new vocabulary, and we're really trying to think about how it's 4th degree, and we really have the number 2 twice, and then 3, and then 4 that were our solutions. So we really have 4 solutions here. So we're talking about the fundamental theorem of algebra today, the degrees of these polynomials. So there's a lot of things going on. So that's why I'm adding in kind of that extra piece. So our solutions are x is 2, 3, or 4. So next we're looking at Descartes' rule of sign. So you could also use this when you're finding zeros, but it's a little more time consuming. And so usually in math, we treat it kind of as a one-off, like you do one problem on your test about Descartes' rule. So it says the number of positive real zeros is equal to the number of changes in sign of the coefficients of f of x, or less by an even number. Number of negative real zeros of f is equal to the number of changes in sign of the coefficients of f of negative x. So negative real zeros, negative x. Positive real zeros, positive x, right? So there's a pattern there. Or is less by an even number. So let's think about or less by an even number and see what that means. And number may or may not be spelled correctly. So let's think about if we start with let's say blank sign changes. Okay. So let's say I have 3 sign changes, or less by an even number would be that there would be 3 or 1, because an even number is 2 and 1 is 2 less than 3. So I'm counting down by even numbers. So it's like skip counting, right? Or skip counting. Maybe we should write that here. I don't know if that's really a math term, but that kind of makes sense to me. If I started out with 8, that would mean I could have 8 or 6 or 4 or 2 or 0, right? I would keep counting all the way down till I get 0. This one I can't count down to 0 because 0 isn't less than 1 by an even number. It's less by 1, and 1 is not even. So 0 would not belong on this list. So let's think, what if we had 4? If we had 4 to start with, 4 sign changes, that would mean we would have 4 or 2 or 0. If we had 7 sign changes, we would have 7 or 5 or 3 or 1 zeros. So that's what we mean by or less than an even number. I think it's just worth kind of talking about that vocabulary. That's the part that most students get hung up on. So for example 2, we're going to describe the possible real zeros. So we need to look at sign changes. So first we're going to look at sign changes for f of x. That's the positive. So it starts out as a positive x to the 4th and switches to negative. That's 1. Then it stays negative. Then it goes from negative to positive again. So that's going to be 2 sign changes for f of x. For f of x. So because there's 2 sign changes, it means that there are 2 or 0 positive real zeros. And this year we're just going to list positive real zeros, negative real zeros, just the possible real zeros. We're not going to worry about imaginary and kind of filling in the blanks. So now I want to think about f of negative x. So that means my entire equation, I replace negative x's for x's. And then I need to go through and simplify, because I know anytime I raise a negative to an even power, it's actually going to end up being positive, so it won't change. And anytime I have an odd number, it'll actually be negative. It will change some stuff. So let's see, f of negative x, if I have a negative x to the fourth, it's just x to the fourth. But here, when I raise a negative to the third power, it'll be negative. So negative and another negative will end up being plus 3x cubed. And then this is going to be minus 5x squared. Again, even power, it's going to just stay positive. Oh, but this one will change too. 2 times negative x will now be minus 2x and plus 7. So now we want to look, now that we've simplified, we're going to look for sign changes again. So it starts out positive, it stays positive. Now it goes from positive 3 to negative 5, so that's a change. Stays negative and then goes from negative to positive 7. So we have 2 sign changes also for f of negative x, which means we are going to have 2 or 0 negative real zeros. And we're going to leave it at that. We're not going to try and think of like, well, if there's 2 positive and 0 negative, there must be a couple imaginary. We're just not going to worry about that this year. We're just going to do Descartes' rule, just a real simple way. The other thing I want to draw your attention to is it says possible real zeros here. And that just means that we are using, the way it says describe possible real zeros, that just means to use Descartes' rule. And on your test, I'm going to actually name the rule. So it will take away any ambiguity. I'm worried that you'll see possible real zeros and you'll think of P's and Q's, and that's not what we're talking about here. We're talking about describing them, like how many could there possibly be. We're not saying list possible rational zeros. Those are different things. Rational means fraction, right? Real zero means I could have square roots or something instead. And describe versus list, I think, are different too. So we've got the fundamental theorem of algebra. So the fundamental theorem of algebra is just that if we have degree n, we have exactly n zeros. So remember, some of them could be imaginary, some can be repeated, but there will be exactly n if you take that all into account. And that makes sense to us. Linear equations are degree 1, they've always had 1 equation. Quadratics are degree 2, they've always had 2 solutions. Sometimes it's repeated, right? When we've got a perfect square, sometimes it's imaginary, but there's always been 2. Linear factorization is just basically if it's n degree, it has n factors. We can write it in factored form. So n degree, means there are n linear factors. So basically we can always write something in factored form, even if it's kind of creative factoring with I or with square roots. It does say that. There are some complex zeros. We can still work towards factoring those. And we're going to just briefly cover that. So here I want to write a function as a product of linear and irreducible quadratic factors. So if I want to start factoring it, and it's 4th degree, I'm going to have to do P's and Q's. That's really what they're telling me. I'm going to have to find some factors that way. Next, we're going to make it the product of linear factors, and then we're going to list all the zeros. So at the end, we're going to finally solve. So for now, I'm just going to list my P's and Q's. P's are a factor of 40, Q's would be factor of 1, so my Q's are at least easy again. So P over Q is plus or minus, let's see, 1, 2, 4, 5, 8, 10, 20, and 40. I think that's it. And I didn't write plus or minus in front of each of them this time. So we'll just have to remember that. So like I said, I usually start with 1. It's boring, but I like to keep track and I like to do it in a methodical way. My powers go 4, 3, 2, 1, 0, so no placeholders, no zeros necessary. All right, let's try this. Let's see, 1, 1, 8, 8, 22. Okay, so I'm noticing something here. These are all positive. And I know if I try 2 or 3 or 4, there's no negatives here. I'm just going to keep getting bigger and bigger positive numbers. And that's actually what an upper bound looks like. Let's go ahead and switch colors. So because these are all non-negative, 1 is an upper bound. Also that it's greater than or equal to 0, right? 1 is an upper bound. And so now we have effectively cut our guessing in half. We know that we should not try any more positive numbers. We should only try negative numbers. So it does help us to recognize those a little bit. Not always, but it does sometimes. And I think that's the best use of that. So I'm going to try -1. I'm going to switch back to my blue again. So let's see, 1, 7. And I usually draw a line when I find something that doesn't work. I don't want to, oops, almost wrote a 48 there. I don't want to obliterate it. I want to see what I've already tried. The students I see that mess this up the most, they don't have any kind of pattern for guessing. They just kind of make their guesses all over. If this was doubled, it would work, huh? Makes me think that maybe -2 will be lucky. And they don't keep track of what they're guessing. They just guess in a random order. They're not working from left to right or anything. So it's hard if you make a mistake to tell what to try again. You know, maybe halfway through you're like, oh shoot, I should have a 0 in there, but then you don't know what you've tried already. So by never erasing it and just, you know, continuing that and kind of working through them in a pattern, it keeps you from making some of those mistakes. And it gives you just a way to check. Wait a minute, that's not right. That should be an 8. I almost multiplied wrong, which would be bad because I think this is going to work out. All right, look at this. I've got a reduced polynomial now, or a depressed polynomial. So I started out with, let's see, what degree did I start with? 4th, so now I'm down to 3rd. So now I have x cubed, let's see, plus 5x squared, plus 4x plus 20. And I'm noticing on this that I have like a 1 and a 5 and then a 4 and a 20. 4 times 5 is 20. So I'm kind of thinking I could factor this with factor by grouping. So I'm going to try that. It's going to be a lot easier than continuing to guess until I get a number right. So x squared times x plus 5. If I'm wrong, I just erase it, right? 4 times x plus 5. Look at that. The x plus 5s, those quantities match. So it is going to be x squared plus 4 times x plus 5. So for part A, they want us to factor it, right? Factor the entire polynomial. So I have, let's see, I had a -2 that was a solution. So that means the factor is x plus 2. And we have an x plus 5. And we have an x squared plus 4. So that is an irreducible quadratic factor. So for B, though, I want to make it all linear factors. So that means for part B, I'm going to just go ahead and factor x squared plus 4 anyway, because I can with complex numbers. So this will be an x plus 2 times x plus 5. And then remember, this is going to be x plus 2i. I'm running out of room, x minus 2i. So I've gone ahead and factored it. So for part C, it says we are going to list all zeros, which means we're going to solve. So I'm going to write that 0 equals x plus 2 times x plus 5 times x plus 2i times x minus 2i. I gave myself a little more space this time so it fits. So I'm going to go through and solve it. So I've got -2 for x. I don't think I left enough room again. I've got -2i, and then I'm going to also have a positive 2i. So I'm going to list out that my zeros are -2, -5, -2i, and positive 2i. So next we have the conjugate root theorem. So lots of theorems today. So what this is really saying is in order to have a real coefficients, if we have a plus bi as a root, we also have to have a minus bi. So in order to have real coefficients, we basically, it's like we had to have something where they cancel each other out, right? We know if we multiply these two guys, we don't end up with any more imaginary numbers. And that's what we're talking about here. In order to not have imaginary, if we have one imaginary root, there have to be two, they have to be conjugates. So examples of complex numbers and conjugates. Let's do examples and then conjugate just really quickly. And for a conjugate, we're going to change the sign on the imaginary part. That's basically what we're doing. So if I have 1 minus 3i, when I take the conjugate, now it's 1 plus 3i. If I start out with negative 2 plus 4i, I don't change the negative 2 to a positive, I change the sign on the 4i. So now it's negative 2 minus 4i. If I start out with a 5 or negative 5i, let's say that means I now just have a positive 5i. So in order to have real coefficients, if one of the roots is negative 5i, the other one has to be positive 5i. If one of the roots is 1 minus 3i, the other one has to be 1 plus 3i. So in order to have real coefficients, if you have one root, you have to have the conjugate. So for 4, and there's a lot of different ways to approach this. I'm going to approach it kind of from the very beginning. I'm not going to approach it with factors. I'm going to approach it with solutions. So they're telling us all the zeros. If we have 2 minus I as a 0, then 2 plus I is also a 0, right? That's that conjugate thing, the conjugate root theorem. And so I'm going to start out by saying, well, if these are all my zeros, then I'm going to write x is negative 1, x equals 2, x equals 2 minus I, and x equals 2 plus I. So now I want to express these as factors instead. It's kind of like I'm doing zero product property backwards. So then I'm going to write that x plus 1 equals 0, x minus 2 is 0, x minus 2 plus I equals 0, and x minus 2 minus I equals 0. So because all of these factors separated like this could equal 0, then I'm going to multiply them all together and have them equal 0. So like I told you, it's kind of like we're doing zero product property backwards. And a lot of times we will actually just start the problem from right here. We'll recognize that if those are the zeros, then these are the factors. But I kind of wanted to start it from the very beginning. So if you were confused, we weren't starting in the middle. So now I'm going to do some factoring tricks. Or multiplying tricks. I'm going to multiply the first two. So x squared, let's see, a minus 2x plus 1x. So minus x minus 2. And then on the second one, I'm going to use this pattern where I have x minus 2's in both of them. And then I have a plus I and I have a minus I. So I know if these two match and these two match and one's plus one's minus, I want to think about the structure. So think about this. Think about this. If I have an a minus b times an a plus b, I know I'll have an a squared. I know the middle stuff will cancel, right? Because they're the same, but one's plus, one's minus. So I'd have plus ab minus ab. And then my second term will end up being minus b squared. So I end up with these squared minus these squared. So that's the pattern I'm going to use here. So now I'm going to write that I have x minus 2 squared minus I squared. And these should probably be brackets. It would be easier to manage this all. So I'm going to leave my x squared minus x minus 2 for now. It's just going to hang out. Basically, what I was trying to do is getting around just distributing this so many times, right? This is going to make it a lot easier. This will now be x squared minus 4x plus 4 when we expand. I squared is negative 1 minus negative 1 is a plus 1. So we're still going to have a lot of distributing in the end, but it's not as bad as it could be. Let's see, x squared minus 4x plus 5. So now I want to think about distributing all this. X squared times x squared is x to the 4th minus 4x cubed minus 5x squared. I'm going to kind of stack these just to help me keep track of them. Negative x times x squared now is negative x cubed. Negative x times negative 4x is plus 4x squared minus 5x. So see how I'm organizing them in columns to make it easier to add. Then when I distribute the last one, negative 2 times x squared is negative 2x squared plus 8x minus 10. And this whole thing's going to equal 0. And then I'm going to go through and total them up. So we'll have x to the fourth. So we've already found our like terms. Now we just start adding. Minus 5x cubed. Let's see. Was this a plus or minus? I feel like I missed something right here. This should have been a plus. So 5 and 4 is 9 minus 2 is a 7x squared. And then plus 3x minus 10 equals 0. So it says, though, that I was trying to find a polynomial function. So I want to write this as f of x. That's what the word function tells me. So instead of making it equal to 0, I'm going to write it as f of x. And we're done. And maybe I'm saying that too early because there is one last problem. So we are going to use these conjugates in a different way now. So last way we're going to use them is they're going to give us one solution. So one solution is 2i, and that means that the conjugate negative 2i is also a solution. And we know that because it has real coefficients, 1, 2, 1, 8, negative 12, those are all real numbers. So negative 2i is also a 0. So I am going to do synthetic division with 2i, and then I'm going to do synthetic division with negative 2i, and then I'm going to have something that'll be a quadratic, right? Because if I use two different solutions, if I start out with fourth power and I do this twice, I'll be with an x squared. So I'm going to leave myself a lot of space for this, and it's going to take a little bit of scratch work. And I'll bring down the 1, multiply by 2i, and then I add. So now it's a complex number. So now I'm multiplying the 2i times the 2 plus 2i. So this is where my scrap paper comes in handy. So that would be 4i plus 4i squared. Remember, I squared is negative 1. So this is negative 4 plus 4i. And then I add 1 and negative 4 is negative 3 plus 4i. So then we're going to multiply again. So multiply the 2i back times negative 3 plus 4i. So let's see, we have negative 6i plus 8i squared. And remember, again, I squared is negative 1, so we have negative 8 minus 6i. And so now our real parts are completely gone. We just have a pure imaginary number, negative 6i. 2i times negative 6i. So 2 times 6 is negative 12i squared, but I squared is negative 1, so it's really a positive 12. And so we have a remainder of 0. So we can tell that 2i is a factor because we have a remainder of 0. So it's kind of neat the way that's going to check and work out for you. So now I'll use a negative 2i. And my depressed polynomial has the coefficients 1, 2 plus 2i, negative 3 plus 4i, and negative 6i. So we're using those weird numbers now that we had left over. And this point is always really cool because everything's going to cancel out. I'm going to get real numbers. I'll get a 0 at the end. So it's kind of cool as you're going through it. You get to check your answer as you go. So 1 times negative 2i is a negative 2i. And then look at this, 2i minus 2i, those are gone. We just have a real number 2. 2 times negative 2i is a negative 4i. And again, 4i, negative 4i, gone. They make a 0. We're left with negative 3. Negative 3 times negative 2i is a positive 6i. And so we have a 0. So it's really kind of slick the way that works out. I really like the first one, you're kind of worried, but you get a 0 at the end, so you know you did it correctly. And this one, you end up with these real coefficients in the 0, so it's really kind of cool the way it turns out. So we started out with x to the fourth. So this weird one, the 1, 2, and plus 2i, that was a cubed. And now we're looking at squared. So we have x squared plus 2x minus 3. And I think our goal here was factoring, right? Finding all the complex zeros. So let's just write that out really quick. Our complex zeros, that was the first part of the question, are 2i and negative 2i, and now it wants us to factor. So I'm going to factor this little part, x plus 3 times x minus 1. And when I go to factor the entire function, it says linear factorization. So we have a 2i and a negative 2i, so that means an x plus 2i times an x minus 2i times x plus 3 times x minus 1. So I have been talking for a long time now. I know this is a lot of information today. Please work through the homework. If you have questions, let me know, but we can definitely keep reviewing this every day in class.